In this video, we're going to go through the mechanisms for acid hydrolysis and base hydrolysis of nitriles. So just as an overview, the nitrile functional group is a carboxylic acid derivative, and we can hydrolyze that to a carboxylic acid, wherein you'll visualize the carbon of the nitrile is becoming the carbonyl carbon of the carboxylic acid. Note that we need to use a full equivalent of acid to do this transformation. That's because our leaving group, the amine, will ultimately consume the acid. It is not regenerated in a catalytic fashion. So full equivalent of acid is required. The amine byproduct is protonated. Under base hydrolysis conditions, we'll react with NaOH, H2O, and heat. We have a hydrolysis under base conditions to produce a carboxylate ion, and our nitrogen byproduct is neutral. Let's look at the mechanisms. Now, these mechanisms look daunting, but don't let that scare you, all right? Let's apply what we've learned. To begin with, under acidic conditions, we will protonate the nitrogen atom. The nitrogen is then going to withdraw from the carbon, increasing the electrophilicity of that carbon of our nitrile. Water will then attack and break one of the pi bonds of our nitrile. That leaves the carbon and nitrogen just doubly bonded, and the water molecule is added in, taking on a positive formal charge. We then want to deprotonate that oxygen atom to make it neutral. Now that produces something called the amidic acid intermediate, and that is essentially the enol tautomeric form of an amide. Okay. Now, from the amidic acid, what we're going to do is fold down a lone pair, forming a carbonyl, and then we push and break the carbon-nitrogen pi bond here, and we're specifically in that step adding a hydrogen to the nitrogen atom. So we're protonating the nitrogen, and that's generating for us a protonated amide intermediate. Okay, I think that's a good checkpoint intermediate for us. In the hydrolysis of the nitrile under acidic conditions, we go through an amidic acid intermediate, which then gives rise to a protonated amide. And from there, well, you already know this mechanism. That's just amide hydrolysis. So given that the carbonyl is charged positively, water can attack and break the pi bond. We eventually want to kick out the nitrogen component, but given that we're under acidic conditions, we're going to need to do some proton transfers, ultimately making the nitrogen charged positively so it can leave as a neutral leaving group. Looking at that first tetrahedral structure, we have to deprotonate the oxygen atom to decrease its leaving group propensity. We then have to protonate our nitrogen component to make that definitively the best leaving group and ensure that that gets kicked out as a neutral leaving group. Either of the two OH groups can collapse a lone pair, forming a pi bond, which then expels the amine leaving group. And then the amine can deprotonate the carbonyl oxygen, forming your carboxylic acid and your protonated amine byproduct, NH4+. Now, conceptually, we don't use a catalytic amount of acid here because once that nitrogen grabs the proton, it's stuck there. We do not regenerate, I should say, the acid in a catalytic fashion. We need to use a full equivalent of acid to drive that to completion. Recapping that mechanism quickly, we protonated first to increase reactivity of the carbon of the nitrile. Water then attacks and breaks the carbon-nitrogen triple bond, forming a carbon-nitrogen double bond. We then need to deprotonate the oxygen atom to alleviate the charge. That brings us to the amidic acid intermediate. The oxygen is naturally in resonance with the pi system there. So let's imagine collapsing a lone pair from the OH, forming a pi bond. And then we are going to push the pi density from the carbon-nitrogen pi bond, which is adding a hydrogen to that nitrogen and forming a carbonyl, specifically a protonated amide. Now, that's going to be attacked by water. We can attack with water because the carbonyl is charged positive, it's protonated. We then need to deprotonate this oxygen atom to decrease its leaving group propensity. And before we kick out our nitrogen leaving group, we have to charge it positively so that it can be kicked out as a neutral leaving group. We'll then collapse and kick out the neutral amine leaving group, forming a protonated carbonyl intermediate. And then our amine leaving group can deprotonate, forming our carboxylic acid and NH4+. Let's now look at the base hydrolysis mechanism. of a nitrile. Mechanistically, we can attack right away because hydroxide is a good nucleophile. We break the carbon-nitrogen triple bond. Nitrogen is now charged negatively. We then want to protonate the nitrogen in the next step to make that neutral. Notice we're again producing an amidic acid. Now that amidic acid is going to be deprotonated at the oxygen atom that charges the oxygen negatively. Then we're going to fold electrons down, forming a pi bond. And then we're going to break the carbon-nitrogen pi bond and use those pi electrons to bond the nitrogen to a hydrogen, which is coming from water. That produces a neutral amide intermediate. Neutral amide intermediate. That's a good checkpoint. Then from there, we're just doing amide base hydrolysis. Hydroxide will attack the carbonyl carbon and break the pi bond. In the tetrahedral structure that we create, what we just added in is the better leaving group. So we need to deprotonate that OH component and form a dianion intermediate. There's a hella electronic repulsions here, but now the better leaving group is our NH2-. We will collapse the tetrahedral structure, kicking out our NH2- leaving group. And that elimination directly prepares the carboxylate ion. Then NH2- will very rapidly react with water in solution, deprotonating. That would deprotonate irreversibly to form a neutral amine. Okay, so to recap that, hydroxide attacks right away, breaking the carbon-nitrogen triple bond, forming a carbon-nitrogen double bond. Nitrogen has a negative charge. We're then going to protonate the nitrogen atom, making that neutral. That's our amidic acid. And under the basic conditions here, we will deprotonate the oxygen of the amidic acid, charging the oxygen negatively. That will then fold down electrons to form a carbonyl, and we break the carbon-nitrogen pi bond, protonating the nitrogen, producing our neutral amide intermediate. Hydroxide will then attack the carbonyl carbon, break the pi bond, and then we need to deprotonate the OH component, creating our dianion intermediate, and then we can collapse, kicking out our nitrogen of negative charge leaving group. And our nitrogen of negative charge leaving group will very rapidly react with water, stealing a proton, doing so irreversibly, forming a neutral amine byproduct. Now, hopefully those mechanisms didn't feel as daunting as they look, and hopefully that's the case because we've set ourselves up nicely in this video series to be able to process our mechanisms. Now, you can memorize all of these mechanisms if you want, and it's a lot to memorize separately. But I hope it's been clear that there is a logic, there is a pattern, there are rules that we can follow, and we can establish mechanistic rules and parameters, which we've detailed in the last number of videos, that aid us in thinking through these mechanisms. And that actually kind of feels cool, right? It feels powerful. You feel like a whiz, like a straight chem whiz. Because now we can think through mechanisms. It is possible. All right. In the upcoming videos, we will be going through energy diagrams, looking at radiolabeled oxygen atoms. And then from there, we're going to get into mechanisms, practice problems, all the good stuff, and of course, synthesis towards the end. Keep pushing. You're doing a great job. You've got this. Let's get it.